Okay, looks like there is some issue with the live streaming, so I have to started recording the session. Okay, yeah. So, so this is the first session for week 5. So week 4 we have seen the representations of graphs, directed, undirected, weighted, and weighted, all those categories, and then we looked at the traversal algorithms, which are the DFS, BFS. Now, this week we are looking at two important problems. One is the finding the shortest path, and also finding what is known as the spanning tree of the graph. So I'll just share the screen. Yeah. So here is the week 5 content. So the plan for today, I hope you are able to see this OneNote screen, right? Where I have written down these things. Are you able to see what I'm selecting?
Yes,
Yes.
ma'am.
Yes.
Okay. So these are the topics that we have to address this week. I'm not sure how many topics we'll be able to complete, finish today. But we'll just try to finish, as much as is possible, and hopefully giving you the clarity that you need. Okay. So last week we saw the DFS, BFS, and we found that most of the graphs that we considered were unweighted graphs, right? So in the DFS and BFS, so in the BFS algorithm, we also said that okay, if you want to find the shortest path, say from a given node to another node, you can just run the BFS algorithm and you will get the shortest path. So at that point, the underlying assumption was that every edge had a length of, say, unit length, say 1, or every edge had the same length, right? That was the underlying assumption, and is the um, this is what would give you the shortest path for a given source destination pair in a given graph. So generally in real life cases, most of the times the weight you cannot the distance between or the weight that you want to associate with a certain edge, right? That may not be unit weight in the sense that all of the edges may not have the same weight. Say, for instance, you want to compute the distance, right? This is a typical example that we use for this kind of graphs. So, if you want to find the distance between, say, Chennai to Mumbai or Chennai to Delhi, there are so many ways that you can take, right? You can go via Bangalore, you can go via Hyderabad. There are so many routes that you can take. And you want to find the shortest. So, if you just assume that Chennai to Bangalore has the same distance as Bangalore to Mumbai, it just doesn't make sense, right? The same way to Hyderabad or whatever. So, you have to associate a weight which will give you an indication of what is the effort or what is the time or what is the distance, right? There is a relative difference in weights between the edges in the graph. This is where the weighted graphs come into picture. So, in the case of finding shortest paths for the cities, right? So as we have as I just mentioned the example, this distance between two cities we can associate it as the weight. Or if you want to associate the time required, or you want to indicate the money, like the if it's some taxi or something, if you want to associate the fare, right? It may not be directly proportional to the distance all the time. In certain cities they charge you really more, and certain villages it's much less. And I mean, it's possible, right? It may not be proportional to the distance, so it may be the amount that is being charged. So it can be, you can actually associate a meaningful, or rather a realistic meaning to the weights of the graph. So in many scenarios, we want to find the shortest path. This is a minimization problem. So you might ask, what is the other counterpart, which is the longest path in a graph, right? So that's a hard problem. In a simple graph, like finding the longest path is a hard problem. Whereas shortest path, you can have an efficient algorithm. So let us just I'll just denote one. I'll just show you one simple example of the weighted graphs. Mm, it's a weighted. So you have weight 8, 6, 4, 10, 22, 80, 110, 2, 5, 6, 3. So this is the weighted graph. We are associating every pair, say every pair UV or every edge E, right? This has a weight function associated with it. So whenever we define a weighted graph, say we say G equal to V comma E, we also define what is known as a weighted function, which is from every edge there is a real number. So this R indicates a set of real numbers. I hope you know that. This R, right? You put this R. It's different from the rest of them. Yeah. So this is a set of real numbers. So for every edge, you associate a real number with them, and that is a weight function as you call it. So here, if you have say 1, 2, 3, 4, 5, 6, 7. So edge 4, 6, right? This will have a weight 2. This one. Okay. Yeah. So this is the weight function that we have. This is the weight function. I mean, for every edge we associate this, and that we get it as a function. Okay. So this is a representation. This is a general representation for a weighted graph. In the case of Python, or rather in the applications that we have used, how we represent the um weighted graph. So, for instance, in the adjacency matrix, we give the. I have to download it as a PDF. Just give me a second. I have to download it as a PDF. Just give me a second. Otherwise, I cannot write. Is this clear now? I mean, is this visible? Sorry. The matrix representation is it visible?
Yes, ma'am.
So this is a representation that we use. Say, for instance, you have this three tuple, right, which will indicate that this is the source vertex, or rather, the one part of the edge. This is the other part of the edge. That's the other vertex. Say, so this is what I okay. This is the edge 0 to 1, and it will have weight depth. That is what this one means. It doesn't have to be this directed edge. We interpret the. I mean, we can interpret directed edge by saying like, okay, you have this. If it is an undirected graph, you can give this edge because it's bidirectional. Right? For every edge, you can have the other direction also. In the case of undirected graph, this is equivalent, right? This is 0, and this is 1. This is negative. Okay. So this is what the representation that we use throughout. I mean, this presentation, whatever we're studying, and we use a NumPy for initializing the array, which sorry, the three-dimensional matrix which contains this weighted. So what does this representation mean? So you have a three-dimension, right? The first dimension is the so you have something like this, right? 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, and each will have say 0, 1, and say 1 comma uh, say 20 or something, okay, or 0 comma 0. Sorry, here doesn't make sense because it's 0, 0. So here there is like it's a 0 entry, right? So it doesn't make sense. So suppose there is a here in the same example, right? 0 to 1, 1 to 0. So if there is an edge from 0 to 1, then this entry, right? So this will have 0 comma 1 and 1 comma 10, which means that the 0 entry, So this is a three-dimensional matrix, right? So the two-dimensional matrix which shows the rows and columns showing the source vertex and the destination vertex. And this two entries, right? The first one, this is the third dimension of the matrix, the 0 and 1. If this is 0 and if I put a 1 here, it means that there is an edge that exists from 0 to 1. And with respect to 1, whatever is that edge weight, that is what I'm putting it as in this three-dimensional matrix. Is this representation clear or am I confusing one second?
Please, once more, ma'am.
Yeah. So for
There's a
each
value.
of these,
How to correlate
yeah.
the value.
So okay,
Please give
you consider
please
this
give
entry. Okay, you consider this entry. I'm going to show it as an enhanced way. So this we
yeah, yeah.
have 0, 1 and 1, say 10. So if I say 0, 1, see here for each edge that is there in this list, right? If there is an edge here, then the 0 part of that matrix, right? I'm going to assign it as 1, and the 1 part I'm going to assign the actual weight. That is what this means. This is a three-dimensional matrix. Got it? Two-dimensional you understood, right? And the third, each entry is another list here, or rather another matrix here, which is 0, 1, 1, 10. This is a matrix that we have. No, sorry, I don't confuse it.
Ma'am,
Yeah,
ma'am,
sorry.
give an example. Ma'am, give an example
Yeah,
here.
example is what I'm saying. No, see 0, 1, 10 is there, right? So in the case of here, W 0, 1, which stands for the edge 0, 1, the 0 entry will be equal to 1, and W 0, 1 of 1 will be N.
Now, what is 0 and what is 1 here? Suppose, give another nomenclature, ma'am. 0 and 1. I'm not confused. I'm not getting this. How this value is being correlated with the weight?
Okay, let me show you 1 second. Give me a second. Sorry, I'll just show you 1 second. So suppose you have a simple graph like this, okay?
Yeah.
Which is 0, 1, 2.
Yeah.
Directed for the convenience, okay? So you have a matrix here, right? Which is 0, 1, 2, 0, 1, 2. Okay?
Yeah.
When it was weighted or unweighted, we had a 0 or 1 entry. That's it, right? If it
Yeah,
was
yeah.
just unweighted, then we had, because there is an edge from 0 to 1, we had a 1 here. And for 1 to 2, we had an entry 1 here. Everything else was 0. Is this correct?
Yeah.
This is clear, right? In the case of weighted vertex, we want to indicate the weight somewhere, right? We want to give the weight somewhere.
Yeah.
So we want to check, see, we could have directly given, say 0 to 1, we could have given 10, and 1, 1, 2, we could have given 8. But what happens is, how do you know whether 0 is actually the weight of that edge? Right? You don't know. What you mean by this 0 is that there is no edge. But suppose there is an edge with weight 0, what do you do? Got it? Are you getting
It is 0. If the weight is 0, then it will be confusing. Otherwise, it is okay.
Yeah, that's what I'm saying. So weight could be 0. How do you know weight is not 0? So to avoid that confusion, we are adding another dimension to the matrix. So instead of two-dimensional matrix,
whether this is the only reason that we are getting the third dimension, because 0 will confuse with the value of the weight.
Any value you initialize, it could as well be the weight of that edge.
Okay.
So to avoid that, you have a 0, 1 entry and the 1, 10 entry. If it is the other one, this will all be 0. Right? So this 0 actually denotes that there is no edge between. So it does not even have to look at the one part of it. Whatever algorithm is checking, right? So in the algorithms that we have, we are always checking whether this part, right? Say u, v, this part we are always checking whether it equal to 1. Sorry, this one. Right? If this is equal to 1, right, it means that there is an edge. Only in such case we need to process that edge. Got
Ma'am,
it?
I
No, the
have a
zero.
doubt actually. 0 and 1 will be row and column. Then 10 can be easily located in matrix. Na? Why we require to put 0, 1
This
and 1, 10?
this example is what I'm saying, right? This is what you're saying. We can have this representation is what you're saying. This first one.
Yeah, ma'am. 0, 1 and weight is 10.
Yeah,
Directly we can.
that's what I'm saying. This is the first suggestion what I've given. But what? How do you know whether this is actually the absence of an edge or the actually an edge with weight zero?
Ma'am,
Yeah.
like I didn't start with the week 5 so I mean so nicely. I didn't read it, but I just started watching some initial videos. So I just watched one of the video today, and if you can just help me out with that. So in this particular example only, the first matrix which you have drew, in this, can't we write, for example, there is no edge between let's suppose 1 and 0, right? The one, like the second row, and the
Yeah.
zeroth column, right? There is no edge, so that's why you're mentioning 0. Now there is a way where we can write, for example, there is an edge between 0 comma 1, so we can write 1 comma 10. That means that's how sir told us over there. That means there is one edge and the weight of that edge is 10. And for the rest, where you've written 0 0, we can write 0 comma 0.
So
That means
that representation also you can use. There is no problem. But I'm not sure if you will get into trouble with certain cases where you have to check for the existence of edges. So how will you do that? So suppose you have say, so what you're saying is you will have something like 0 comma 0 here, and this will be 1 comma 10. Is it? So
yeah,
what you mean?
yeah. So that means
And
there
suppose this
exists.
was 1, then what you're saying is something like this, right? 1 comma 0. If there was an edge and it has 0
And the
weight,
weight
then it
is
will be
0.
something like this. Yeah.
Right.
Yeah, that also you can take. There is no problem. But see, I'm not sure like whether, I mean, there are certain situations where we are actually checking for the presence of an edge. I'm not sure whether that will, but here you can actually check the first. Um, you see, this one is what I'm talking about, right? Cases like this one. So you can actually try with that. I think it is possible, but we have just followed this convention, is what I'm understanding. Okay, but you have to clearly distinguish between. The point is you have to clearly distinguish between when there is no edge and when there is an edge with weight zero.
Okay. Ma'am, could you please explain the line number 6 and 7 of code just once again? That's slightly confusing.
Line 6 and 7 of?
This one only, wi, comma j, comma 0 is
Okay,
equals
just
to.
1 second. Let me just refresh. Yeah, this one, right?
Yeah. The 6th and 7th line.
Yeah. So what is for ij in the d edges? This, etc.
Yeah.
Right? For each such tuple, 3 tuple, right? What you do is w of 0, 1, 0 equal to 1, w of 0, comma 1, comma 1 equal to 10. That's all what you're doing. Suppose there is no edge from say 1 to 2, is there? 2 to 1 is there? So let us see 1 to 3. So you will have w of 1 comma 3, because everything is first initialized to 0, right? All entries are initialized to 0. So this will be 0 and this will also be 0.
And ma'am, what does this 0 and 1 implies? Like I comma j comma 0 and I comma j comma 1.
No, it's just some symbolic representation, just to denote that this is actually indicating the presence of an edge and this is indicating the weight of an edge. That's all.
Okay, so the first line, the 6th line is basically it tells whether an edge exists or not.
Correct.
And
Yes.
that's why you are assigning 1 to it. And the 7th
Correct.
line tells us whether, what's the
What
weight.
is the weight of that edge? Yes.
All right. Got it. And ma'am, what's the and the 4th line? What's the why are we using 2, like size comma 2?
Because the dimension of that matrix, right? It's a square matrix, no?
Yeah, and
So,
then 2.
2 is the third dimension, which is the 0 and 1.
All right. Okay.
So I just have one question, ma'am, here.
Yeah.
So this structure of this W matrix it'll be a list. Within that list, there'll be 7 lists because size
So
is
it's a
7.
3-dimensional array kind
Yeah,
of, right? I mean, you will
yeah,
have to
so-
visualize it that way.
Yeah, so I'm just saying, so within that list, there'll be 7 lists. and within that 7 list, each list there will be
Each will
7
have one
elements,
list. Yeah.
and it will
And
have 2 columns.
each of those will have two
List
values.
each
A list of two
uh,
values. Yeah.
no, it'll have 7 elements with 2 columns. So 7
See, I
rows
have.
and 2 columns.
So is
I
this
think
a
that's
list actually? Is this a list?
it'll come as a list because this is a matrix. No? So there'll be a
Yeah.
list within a list, and there'll be 7 because this the size is 7, and there'll be 7 rows and 2 columns within each list. I think that's what it is. That's why it's 2. So the 2 columns, the column 1, I think
Yeah,
would
that is
be
what this two
the
is the what
edge.
are the third dimension is what I'm saying. This
Yeah.
two
So in
is the third dimension.
you're right. So I'm just
Seven
looking
by
at it in
seven.
terms of the list of in Python. You can run this code. We can see what is the
You
W is
can
equal
try
to
it
n.
out on your own because I don't have the time. I have so many things to try out today,
Okay.
so I may not have the time. Please try out. In
Uh,
fact, I'm not even going to look at the adjacency list representation because there are so many
okay.
things that you have to cover, and we are not even able to cover in 3 sessions. Okay, so I'm just going to
Right
go
now.
ahead. Whatever you have to run it out, please try it on your own. Okay.
Right now.
Yeah. Okay. So this is a list representation. It's very simple. You just go ahead and then have a trial at this. Again, this is much simpler than that. For everything, you add it to a particular list. Okay. So this may be more easier for you to understand first, and then probably try the metrics part of it next time. Okay. Yeah. So okay. So this is for the undirected graph. So for each edge, you are adding the other part of it also. That is, for each ij, you are adding the ji also. That is the undirected graph. Because for every edge, right, 0 and 1, you are actually assuming that there is an edge like this and there is an edge like this, right? So this is what you're trying. So here you will add one edge for, say, suppose you have 0, comma 1, comma 10. Then you are going to add 1, comma 0, comma 10 also. That's all what it means. Weighted undirected graph. Okay. Yeah. Yeah, same thing for the list also. Okay. Now comes the shortest path. Okay. So as I was just mentioning, right? So in all practical scenarios, we have the edge weights indicating some parameter that we want to kind of, we want to find the sum. So how do you find the length of a path? So suppose you have. So this is just to give clarity on the definition of what a path is. Okay. So say suppose A, B, C, D, G. Okay. So suppose you want to find the path from say A to the path A, B, D, E, and G. The length of this path is going to be 2 plus 5 plus 6 plus 8. I'm just mentioning it for the sake of completeness. It must be very evident for you. So the the edge AB is of weight 2, BD is of weight 5, D is of weight 6, EG is of weight 8. So the total length of this path will be 13 plus 8, 21, right? Yeah. So this is the length of this path, right?
Yes, ma'am. Yes, ma'am. Okay,
Yeah.
ma'am.
So this is just for completeness, those who are not aware of what a path is, right? So this is just the sum of it. Okay. Now our purpose is like you are given one source. Say suppose A is the source here, okay, and you want to find the A is the source here, and you want to find the shortest path from A to every vertex in this graph. Okay, every other vertex in this graph. Of course, the distance to A itself is assumed to be 0 because we do not allow loops in this simple graph. So this distance is 0, right? For every other vertex, we want to find the shortest path. So that's the problem here. And for this, we make use of two algorithms. Let me just clear this. Okay.
Shortest path to each and every node.
Yes, you are given a source. The source is given. You want to
Okay.
find the shortest path to every other vertex in that graph.
Okay.
Okay. So the Dijkstra's algorithm, right? This algorithm. This is actually, we use it on what are known as graphs with non-negative weights. Okay. What do you mean by non-negative weights? So now all the graphs that we saw just now, the examples, right? It was all positive weight. What happens if the graph had weight something like -1 instead of a positive value? So in such a case, the algorithm that we are going to see now does not work. This algorithm totally assumes that these are non-negative weights. Okay. So let us see the Dijkstra's algorithm first. So I hope the representation is clear for all of you. We'll just go ahead with the algorithm. Okay. So consider this graph. Okay. It has. Let us assume that the source here is, say, source is the vertex 0. Now you want to find the shortest path to 1, 2, 3, 4, 5, all these paths. Okay. So how Dijkstra's algorithm works is, so in the exam, the lecture sir is actually talking about, assume that these are all like oil pipelines, and you're starting a fire in one of these, the source. Okay, so you start the fire here, and assuming that the fire travels uniform speed throughout this pipeline, you want to find out which are the vertices that get burnt first, and then the vertices which are burnt, you assume that you have found the shortest path till there, and then you go. I mean, you kind of propagate it, right? You propagate it to the nearby neighbors, and whenever the fire reaches a junction, it will actually get distributed to all the branches that are coming out of it, to all the neighbors of the graph, right? So again, once a fire reaches the nearest vertex, that node also gets burned. So that's some analogy for you to understand it easier, like how the algorithm works. So in the case of, I'll just take the code of the.
This burning of the burning algorithm is applicable in all the graphs, or there is generic way.
Sorry, I did not understand. Generic, all
Burning,
graphs
where
meaning.
in the example, in the lecture, it is just burn 1, burn 2, burn 0, like that. Is it the generic way to solve any graph?
No,
Burning.
this is just an analogy for you to understand. That's it. It's not a
Okay.
method for you
Okay.
to solve anything. It is more an analogy
Okay.
for you to
Okay.
understand. The
Okay.
actual
Okay.
solution actually happens what is given in this algorithm only. So,
Mm-hmm. Okay.
okay. So how we
Okay.
start out with this is, so you have the source here, right? Source is here, and then what you do is you initialize all the distances with infinity, right? So this is a basic algorithm. Okay. You have you assume that the distance is from 0 to all these vertices is infinity, because what you're going to do is, this distance you are actually going to compare with some new distance, say some coming from some other path, and then you're going to compare with this. So you want this first value to be as large as possible, and you say that it is infinity. So practically when you're doing a program, it is not possible to have the infinity value. So you find some values. If you're sure that this value will not exceed say 100, then you can set infinity as 1000. But if you're unsure as to whatever values these could take, then you'd possibly take the largest value, largest entry in the matrix, multiplied by the total number of rows, right? Because that's a maximum path, the maximum. Okay, how do I, maybe I'll just explain it. Say suppose this is the path here. Let's say I have something like this. Okay, so if I want to start from here, say this is my source and this is one of the vertices. Okay, so why I'm setting infinity to what this value? So this should be the code. This is the initialization of it. So what we are doing is, these are all like the whatever are given by the numpy. I mean, sorry, this, yeah, numpy, whatever it is, using that you are actually calculating. So infinity, you are setting that whatever is the max entry in the matrix, that many number of times you multiplied with the rows. So the graph that I have shown here, right? Here, suppose you had say 100 here, and here you had 8, 6, 4, 12, 3, 2, 1. Then what you're going to do is I am going to assume that my largest path. So what is the maximum length of any path in this graph? What is the
100.
largest?
100. It is 100.
No, 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 no. I'm talking about the length of the path, not the edge. What is this maximum length of the path that is possible? Say, suppose it was an
Okay,
unweighted
S.
100.
graph.
100.
Unweighted
100
graph.
plus
Suppose an
8.
unweighted graph. What is this maximum length possible?
100 plus 8 plus 4
8
plus
plus 4
12 plus
plus
2 plus
12
4.
No,
plus
no,
2.
hold on, hold on. 1 second, 1 second. 1 second, hold on. See, suppose this was an unweighted graph, right? What is the maximum length of any path possible? Between any pair of edges, that is okay. But what is the maximum length that is possible?
N minus 1.
Yeah,
N
n
minus
minus 1.
correct. Because if you have more than n minus 1 edges, right? That's why suppose you have more than n minus 1, right? What it means is that there is a cycle in the graph. Cycle in that path. And for a path, it cannot have any cycle. So for an unweighted graph, the maximum length of any path in that graph is n minus 1. Okay, so if you take something like this, right? So maximum length is because you want to
Cycle.
connect, want to have the every vertex at most once in that path, right? So that means that you have n vertices, and between two vertices you have one, and these two are not connected. So you're missing out one edge, and that is the n minus 1 edges. This is the maximum possible. Okay,
Yeah,
so
yeah.
what we are doing is to calculate the infinity, right? You are taking so what do you mean by n minus 1? What is a so suppose we say this is a unit weight. Say 1 is a unit weight for all of these. What does it mean? The length of the total path is n minus 1 into 1, right? Correct. That is the
Right.
length of the weight of this path. So, but instead of 1, we have different weights here. So what can you take as a maximum length of the path is all of this you assume that it is 100 because 100 is the maximum possible here, right? All of this you assume it is 100, and then for each, so because you can have only n minus 1, so n minus 1 into 100 plus 100. So this you can actually take it as the maximum value. This is no path can exceed more than this. Even if all edges in this longest path are of size 100, okay, of course you can have plus 1 just so that it is not equal, right? You want one more than the equal. So you can have, if even if all the edges in this path have weight say 100, this value will still be one higher than that. So infinity you can actually programmatically set it to some value which you're sure will not exceed the longest path. If you know that it can only go to a certain limit, say for instance you want to find out all the say you have a say set of 5 cities, and you know that the maximum distance between any of them can be say at most 1,000 kilometers or something, then you can have the infinity as say 1,500, right? So as such, infinity doesn't have a proper definition, but we give it some definition by making use of these kind of
But
these
in the
kind of
code, we are
shortcuts.
multiplying with the number of vertices, right? 100 into number of vertices.
Yeah, so it's as much, see, as good as
Right, I
like
agree.
n is the number of vertices only, right?
Yeah.
So n minus 1 into 1 and n into 100 will definitely be more than that, right? Yeah, so you can, yeah, I mean, you can do a fine tuning and see what exactly is the infinity, but that is not required. You only need an approximate value, and you know that this will definitely be an upper bound, right? So, yeah. Okay, so that's what we are going to. So theoretically, you can say that this is infinity, but when you are doing the program, you have to have some value which you are sure that will be the largest value, which will not, none of the lengths will exceed that value. Okay, so that's how you start off with. Now, how does Dijkstra work? Dijkstra algorithm works. Okay, so for that, I have to show
Man,
you the initial session. Yeah.
this infinity is for the cost of the path we will follow. right?
Yeah. So see, before we start, right, we want to initialize the distance from the source to all these vertices, because now what you're going to do is you're actually going to improve that distance. Like, you're going to reduce the distance
Okay,
in every
okay, okay.
iteration. So
Oh,
for
got it.
that, yeah, you should have a comparison which is
Got
much later. So if you compare it, whatever you are computing should be less than that. That's why you're starting off with
it, got
infinity.
it, got it, got it,
So in
ma'am.
the case of maximum, if it was a maximum path or something, right, you should have the other side of it. Like, I'm not even sure, maybe some minus value. If you know that there's a negative value, then you should go to the other extreme. But longest path is a hard problem. So let's not worry about it now. Shortest path, so here you initialize it to infinity. Okay, now I'll just show you the code here. Yeah, so this is the infinity that you have initialized, and this three tuple, right? This is the number of rows and columns and the 0, 1. That's it. Now you have two dictionaries here. One is visited and the other is distant. So visited is just what you have seen in the DFS DFS, right? So whenever you have visited and you're saying that, okay, I'm not going to handle this vertex anymore, I set it to true. That's all what visited does. The distance is a dictionary, right? So what does it do is, so the source is very clear, right? The source is well defined. You don't have to worry about the source. All it is going to say is that, say to vertex 1, what is the distance? Say D1. Okay. Then for vertex 2, what is the distance? Vertex 3, what is the distance? This is what distance. So with just one vertex, why is it defined as, this is S comma V1, right? This is the distance S comma V1 that we are talking about. Here S comma V2 is what we are talking. But because S is implied, we are just having the destination vertex, whatever, and then the distance. So that is what is there in this distance dictionary. Okay, both of them we are initializing it. And then, yeah, visited of each vertex, we are setting it to false, and then distance is set to infinity. Then the distance of the source vertex is set to 0, because that you know for sure that it is going to be 0. Right? Now the remaining code is what I have copied there. Okay, so I want to explain it from this. I just don't want to clutter it with the initialization. So initialization is clear, right? Every node except the source, we have set the distance as infinity. For the source, we have set it to 0. And including the source node, we have set the visited to false. That's what we're going to start out with. Okay, so that's the, yeah. So this is what I have copied from the, after the initialization part, whatever is there, this
But
is
this
what I have.
visited of the
Okay.
source we are doing inside the loop.
Yeah. Distance is outside, visited is inside.
Okay.
Yeah. Okay.
After that, you are coming here, ma'am, in the next step
Yes,
from that
exactly. The
code.
same thing I have copied
Okay,
it. You
okay,
can
okay,
just
got
look
it,
at
got it,
it.
got
Yeah.
it. Okay, okay, got it.
So that
Okay,
it
okay,
is. I
okay.
mean, otherwise, I cannot show it in one screen. So that's why I thought I'll just
Yeah,
show
yeah,
you
yeah,
the
yeah,
visuals.
yeah. Okay, 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 got it.
Yeah. So here, yeah. So this first step, what you're going to do is, you're, but for all, what you're going to do is for all the vertices. What do you mean by number of rows? Number of rows and number of columns is nothing but the number of nodes in the graph,
What
right?
is it? What is it? Yeah.
Yeah, number of nodes in the graph, right? Yeah. Okay, so for this range will be from 0 to 5, correct? For u will range from 0 to 5. Is it correct? So the first value of u is 0. 0 is this vertex, right? Now you want to see the distance of v for v in range rows if not visited of v. What are you doing here? For all those vertices which are not visited, right? You consider the vertex, the distance v, which is the smallest. Okay, for all the vertices which have the visited as false. So here you can actually see that this is all false, right? The distance is this and this is false. Okay, so for all the nodes, right? What is this sentence? This sentence is what I'm trying to explain. For all the nodes which are not visited, you're considering the nodes, or the considering the distance which is the smallest among all these nodes. So what is next to D in the first iteration? Can anybody tell me?
0.
0. Why?
Because it is the minimum. You defined it
Correct.
already as 0.
Correct. This we have distance of 0, we have set it to 0, right?
Yeah.
Sorry, distance of S. Yeah.
S. Yeah.
Distance of S, we have set it to 0, right? Distance of source. So that is a minimum because everything else is infinity, right? Everything else is infinity. So only the source, that is 0. Okay. Now you want to find the next vertex list. What is a vertex list? The neighboring. It doesn't have to be neighbor. Just forget about it. Okay. All the yeah, all the vertices, right, which are not visited and whose distance is 0. So again, all these vertices are not visited. All the vertices, right, from 0 to 1, 0 to 5, none of these are visited here. But the distance of V equal to next D, which is this, is true only for S even now, correct, which is 0. So your next vertex list here is going to be next V list, right? It's going to be 0. Is this okay?
Yes, ma'am.
Okay. Now we have just
This minimum part must once explain, please. The minimum of the distance D for the first
Yeah.
node 0.
yeah. So what is the distance? Distance V is for all rows, right? That is 0 to 5, all 5 of them, correct? Sorry, all
Yeah.
6 of them, correct? So you see what is the distance of 0, distance of 1, distance of 2, distance of 3, 4, 5, etc. And you also have to ensure that the visited is false. For now, everything visited is false. So you're considering distance of 0 is 0, everything else is infinity. So the minimum among that is 0 only, right?
Mm-hmm.
For all the nodes you're considering, see, the source is implied. You don't have to worry. So when you say distance, it's a distance from every node to 0. That is understood. So whether it is 0 to itself or from other nodes to 0, it is implied that the distance of V is actually the distance from the node to 0.
V
And now
is
you're
0 here. V is 0 here, no, ma'am?
no, V can be all the V's, right? V can be 0, 1, 2, 3, 4, 5. All this can be there. Inside this loop, we are saying 4 V in range rows.
Okay.
So it can be
Okay,
0, 1, 2, 3, 4, 5, all of this.
we are iterating through this rows, right?
Rows, correct. So distance of 0, distance of 1, distance of 2, 3, 4, 5, etc. Right? So from among
Yeah.
all these things, you have distance of 0 equal to 0. Everything else is infinity. So the minimum value will be next D because all are not all are no unvisited for now. Right? Not visited for now. Correct? So the next D is
Yeah.
0 and next V list, I'll just make it a little
Okay.
cleaner.
Okay.
Just a second. Yeah. Okay. So I have next D equal to 0. Next V list, right? That's equal to 0. And now I'm saying like if next V list is empty, then I'm going to stop it. Okay, but that is not the case because next V list has 0. So I'm saying next V. I'll tell you what next V list is once again. Okay, that is the minimum of. So there is only one inside it. So I'll just put it as 0. So what is next V list? These are all the vertices which are not visited and at a distance which is the smallest distance I have calculated. All the vertices which are at the smallest distance from the source. So in this case, in this example, there is only one. If you had say two vertices, right? Two vertices which are at two vertices which are say 0. If there was another vertex here which was 0, right? Say 10 or something. This is also 0, right? So if this was there, then this 10 also would have been added to this list. Okay, but
Okay.
because there is only one vertex with weight 0, you have this next V list is 0. Okay.
Okay. Zero distance also must be added. Okay, if it
No,
would
because
have been.
0, here distance of S is 0, right? So,
Yeah. Okay, ma'am.
okay, yeah. So
Got
next
it.
of V equal to 0. And now we are going to set this as true. This statement you can see, you are going to set it as. I have to put this quotes. Yeah, okay. Mm, So what I'm going to do is this, I'm going to set it to true. That's the statement. Okay, the statement. Okay, because visited next to be, I have got it as 0, right? So I'm going to set visited of true is 0. Fine. Now for all v in range columns, if w mat of next v comma v comma 0. So what does this mean? So w mat we have already seen, right? The three dimensional array, whatever. I comma j comma 0 equal to 1 means what? There is an edge, right? That's what this means. There is an edge. So what it is saying is, if there is an edge from 0 to the vertex v, for all vertices it is checking. For all vertices from 0 to 5, right? It is checking if it is it has an edge from 0 to that vertex. If it is there and it is not visited, then you are going to compute the minimum distance. So what you're going to do inside this loop is, now you have fixed as the next vertex to be visited as
In the
0.
next V list, madam, in the next V list, you are checking?
No, V list is still there only. You have actually taken the minimum from the V list. That part is over. Your V list
Okay,
has say 0, 10, 20, whatever is there. You have just taken the minimum, and then that V list purpose is over. You have just got the
okay.
next vertex to visit, some tie breaking. So in generally, what see, because this min, the next v list, we are actually having it as an integer or a whole number, right? The vertices we have numbered as whole numbers. The min function actually makes sense. But suppose you had some other priority, say some objects or something, right? Something for which, say, you had to decide the age of a,
Like name of the city or like that?
yeah, something like that, right? Then probably, I don't know, wherever the min does not make sense, then probably you have to define what minimum is, actually minimum function is. Then you have to actually use a minimum function which will actually define what is some sort of order of some linear ordering of these objects, whatever. You have to specify an ordering of these vertices, and then from among that you have to take the minimum. Okay, for now you don't have to worry about it. It's just to understand the logic, because every vertex is a whole number. I mean, represented using a whole number. When you say minimum of from this list, you are just doing some tie breaking by taking the minimum among that, and you are assigning it. It doesn't matter like which vertex you take, but you are just taking the minimum. Got it? Okay.
Yeah.
So that is, you have said this is true, and for all the other, for all the columns there. I mean, that is like in the column and row are the same here, but you're just saying so that you understand. Here the columns means again 0 to 5 only, right? What you're saying is the next to be is 0, like the vertex that we're considering right now, right? We have decided that this is the vertex I'm going to consider, and from that all the neighbors which are there, these are the neighbors. When it is equal to 1, it means that there is an edge, right? The adjacency matrix, there is an edge. That's what it means. So for all that, if there is an edge and the neighbor is not visited, okay, it has not been set to true, then you compute the minimum distance. How do you compute the minimum distance? You check what is the current distance. Okay, check what is the current distance, and you check the distance from the current node to that edge. So, see, for instance, if you want to reach 1, let me just show this. If you want to reach 1, you can reach from here and you can reach from here, right? Two ways you can reach. What you are saying by taking this minimum is directly, I mean, whatever you have updated here first, compare it with whatever is going to come from this. And if this is smaller, you have to update this one, is what we are saying. I will show you with the example. Just give me a second. Okay. So here for V in range 0 to 1, 0 to 5. Where are the cases where we have an edge?
Vertex 2 and 1.
From 0. Yeah, so it is here. As you can see here, there is one, right? Correct? These two have vertices, right? 1 and 2, correct? Is this clear for everyone? You're just checking whether there is an edge from 0 to that particular vertex, and if it is there and it is not visited, sorry about that. There's some work going on. I'm sorry about that. Okay. So yeah, if it is not visited, then you update. Okay, now you check what is the distance of v. Distance of v is infinity, right? Correct. For each you have to check. So first you check for 0. Then you check for 1. Then you check for 2. Then you check for 3, 4, 5. So you are now checking for 1. Suppose. Now what is distance of 1? Distance of 1 is infinity, right? So here it is infinity. And what is this factor? What is distance of 0? This is next v is 0, right? So what is distance of 0? This is 0 plus the distance between 0 and 1, which is 4,
4.
right? Yeah. So this is 4, correct? So now we have updated the distance 1 as 4. Earlier the distance 1 was infinity. Now I'm going to update it as 4. Okay? Is this clear? This step?
Yeah, ma'am, it is clear.
Okay.
It is minimum out of that, right?
Minimum, yeah. Because infinity and 4 you're considering and it is minimum. Now the next node, like for v in all others you have to consider. Now next is 2. For 2 also this is equal to 1 and the visited is false. Right? We have still not set this to false. Okay. Sorry, we have still not set this to true. It is still false. Don't forget that. And it is not visited. So 2 for 2 it is still not visited. So what you're going to do, you're going to compute the same thing. So here it is infinity and the distance from 0 to 2, which is
2.
correct?
2.
Okay, yeah. So now you have got this 4 and 2 updated here. Now we go for the next loop. So because 3, 4, 5 we don't have edges, right? 3, 4, 5 this is going to be 0. So this if condition is not going to be satisfied. So we come out of this for loop and we go for the next iteration of this.
3, 4, 5 is not required to be checked because v0 is not equal to 1. Is it so?
Correct. Yeah, that's correct. This will be 0, right? Because there is no edge between 0 and 3, 0 and 4, 0 and 5.
Okay.
Got it? No, there is no edge because this one is. Yeah. So we are not going to check.
There is no edge from 0 to 3, 0 to 4, or 0 to right. Okay.
Yeah.
Okay.
Now we go to the next loop of this. So what is next to D now? Now next to D is again you have to look at the distance V now for all the same situation. You just have to look at the distance V for everything, and if it is not visited, you take the minimum. Now, which is the minimum out of these? Can you tell me?
2.
Yeah. Why?
Because it's not visited. Zero is visited, so that won't come there.
Correct.
And we have only 2 of them, which is 4 and 2. Rest is all infinity.
Correct. And the minimum is
2.
Correct? Yeah. So the what set will be there here is 2, 4, and we are taking the minimum of this 2. Is this clear for everyone?
We are in the first line, number second line, next D, because we have got 2 and 4, right?
Correct. Let me just clear this. Okay.
Yeah, please. We have got this distance V as 2 and 4, and we are again going to the upper loop, right? The previous loop.
Again, no, the for loop, the next u equal to 1.
Yeah.
Okay.
Yeah.
So here what we are going to do is we are actually taking all the, again we are considering all the distances and whatever is the minimum among not visited, which is all the distances, not visited distances, right? So we have 2, 4, infinity, infinity, correct? And we have one more, but that is actually visited, which is this 0. This is already visited, right? We set it to true in the last iteration, right? The 0. So that we are not considering. We consider this, and from among this, we take the minimum, which is 2. Okay. Now, this is not the confuse it with the node number.
Ma'am, sorry to interrupt. Ma'am, this 2, 4, infinity is coming from all the edges which are going from 1, right?
No, it is not the edges. It is actually the distance V. Distance V is always with respect to 0, the vertex 0.
Okay.
So you don't be confused with this U. The U is just so that you execute it n number of times.
Okay. So the distance V has only those distances which are from 0.
Correct.
Correct.
Distance, as I told you, right, that
Yeah.
dictionary,
Yeah.
I explained it somewhere, right? I think I raised it. I don't know.
That's okay, ma'am. So the
Yeah.
dictionary has all the distances from 0.
Correct. If you put it as 0, it is 0. To 1, whatever is the distance to 1.
Okay.
2, it is a so
Yeah, that's
everything is S comma V1, S comma V2. It
Right.
is S is implied, so we just represent it as V1. That's it. Okay.
Okay.
So
Okay.
it is doesn't. So whenever distance we are saying, it is with respect to 0 only.
Okay.
So from
Fine.
with respect to this, now the distances whatever we have updated are for 1, 2, 1 and 2 we have updated, so we get the 2. Okay.
Okay, ma'am.
Now I'm going to have the next D is going to be 2. Okay. Now all the vertex lists which are at a distance of 2, this is the distance V equal to all those vertices V which are at a distance of 2 from the source and which are not visited. Here in such a case, from source there is only one vertex which is at a distance of 2 and it is not visited. So what is our next V list? Can
2
someone
only.
tell? 2 only.
2.
Only 2 is there, right? Yeah.
Yeah.
So this next V list is a little confusing, but that is required only when you have 2 nodes with the same length. Okay. Here is the
Right.
new list. Now you have the next vertex, which is the minimum among this list. So again, the whole thing is there's only 2. So this will contain this will be as 2. Okay. Okay. Now we have visited of next we've set to true. So here what we are going to do is here we are going to make
Put
this
the
as
true. Yeah.
so when we set it as true, it means that we're kind of closing this set, this vertex. It means that I'm not going to come back to this because everywhere I'm checking, right? This is visited, everywhere, wherever it's visited only I'm considering. So when I set it to true, it means that I'm done processing with that vertex. Now, if you see the lectures where I'm not going to explain proof of correctness, but there is this assumption where we have computed the short, right? So it's something like this. This part, we've already completed the shortest part. That's the idea. This set of vertices, we've already completed the shortest part. Now we will extend it further. Got it? No, this whatever are the true vertices, right? Those we have completed, we have kind of closed it. Got it? Now,
Right, ma'am.
yeah, okay. Now this is the vertex 2 here, right? Now again we are going through all the vertices starting from 0 to 5 and we are checking whether there is an edge which is there from 2. Why? Because next V is our 2, right? So if there is an edge from 2, whatever are the edges that we have from 2 and whichever are not visited. So what are the vertices which satisfy the criteria? You
We
have
have 1, 3, and 4.
1, 3 and 4, right? Okay. Right. So for 1, 3 and 4, you have to update the shortest distance now. Okay, look at the case of 1, right? So you want to find that what is the distance V of 1? So V equal to 1, 3, 4, right? So first we consider V where V equal to 1. So what is distance of V? Distance of 1?
1. 1.
Why?
Sorry, it'll be
What is distance of V?
2 plus 1.
No. What is current distance of V?
Cor-
See, this
2.
is what the current distance of V is, right? Sorry, this one. This is the current distance of V, right? From infinity, we have updated it to 4. Remember?
Right.
Last time we updated it to 4, no?
4.
Remember?
Right.
Okay. So this value is 4. Can you see the yellow color?
Yes.
Is it difficult to see? Yeah,
No,
okay.
it's visible.
Okay. So this is actually distance of 1. So we have to, this is V, right? V is 1, 2, 1, 3 and 4. So now we are looking at distance of 1. So distance of 1 is what I'm going to update. So I'm taking current distance 1 and distance from which is next V. Next V is 2. Right? So next, what is distance of 2? Distance of 2 is 2.
2, right.
Right? So this is 2 plus what? The
3.
distance, the weight of the edge that is connecting next V and V. Which is, what is next V is 2, V is 1. So what is the weight of the edge connecting this? Which is
3, 3.
1.
2 plus 1.
No, this is 1. The sum of this is 3, correct?
Yeah, sum is 3, the minimum is 3, right?
Correct. So here, now you update the distance of 1 as 3. Is this clear?
Yes, clear, ma'am.
Okay, so now what you're going to do is, where is the black? Yeah, so here you're going to cut this and you're going to update this as 3. Got it now? Now,
Yes, please.
yeah, now you do it for 3 and 4. Because 3 and 4 does not have an edge here, right? Because 3 and 4 does not have an edge, this if loop will not get executed, so these values will not get updated. Sorry, 1 second.
No,
As
ma'am,
an
it will
From 2
go.
it is
we will
there. Sorry,
compare.
from
It
2
has
it is
a-
there. Sorry.
Yeah.
We have to
I'm sorry.
compare, na? 3, 4,
No,
1,
correct.
3
No,
and 4.
there is no
Yeah.
edge from 0, but next V is actually 2, not 0, right? So next V is there at edges. 3 we have to consider, 4 also we have to consider. So we have now not visited. Yeah, this F and this 3 and 4 are not visited, right? It is false. So we look at distance of 4. Let me just erase these things. Okay. Now distance of 3 I want to update it. What is the current distance of 3?
Infinity.
Infinity.
Comma. Distance from next V. What is next V?
2.
Distance to this 2. This is
2
2
plus 8.
plus
8, 10.
correct. So what is distance 3 now
10.
become?
10.
10. So here this will become 10. Got it, right? Now this is the distance. So if somebody has distance of 3, it is equal to 10, not infinity. Okay. Now we
Right.
do it for 4. We do it for 4 like here again we have distance of 4 is actually infinity.
12.
Distance
12.
from 10 is here. So this is 2 plus 10.
10.
Right?
It is 12.
12. So here we update it as 12. So if there is any confusion, please let me know. Okay. So now we come to the next iteration.
Now we have distance from 2 of 1, 3 and 4 as 3, 10 and 12. Now we have to take minimum out of this.
No. It's not the distance from 2 to 3 or 2 to 4. It is a distance from 0 to 10. Sorry, 0 to 3 and 0 to 4. That is what 10 and 12 are. Okay, don't forget that.
Yeah. Okay.
Yeah, that's why I first kept emphasizing, because this is one confusion when I had when I was learning this. Every time I always used to think that is from this, right? So, but that's not the case. It's from the source. Okay. So you have, so in the next loop, what is, okay, I will just erase all of this. Next iteration. Okay. So this is done now. V1, 3, 4 is done. Now we go to the next one, and for the rest, we'll see which is the minimum distance of the one step. So tell me which is the minimum distance now. Now I'm not going to write all these values. I hope you have understood a little bit. So tell me which is the minimum value here. What will be the next D?
3.
3. Why?
The distance of 3, 10 and 12.
One will
because
have the minimum value, right?
Yeah,
Vertex
I
1.
mean distance.
Distance
Vertex
is 3.
1, but next D is 3.
Yeah.
Next D is 3, right?
Right.
Next D is 3. Yeah. Because this is true. This is set to true, right? That is why this distance is gone from now over this thing. So only 3, 10, 12 and infinity are there, out of which 3 is the smallest. So now we look at all the vertices which are at a distance 3 from the source, and that is only vertex 1, right? Only this vertex is there, right? And that vertex, so our next V is also that vertex in this sphere. Okay. Now this visited, we set it to true, right? So this one we will change it to true. Okay. What does it mean? This part of the graph is done. We are not going to consider these nodes anymore. Okay.
Now it is visited. 0, 1, 2 is visited.
Visited, and that part is closed. Now we are not going to process these vertices anymore. Now, can you do as a homework? Can you try to compute the rest of this thing? Is it okay? The
Yes,
same
ma'am,
graph,
okay.
can you try it out?
Yeah.
Because the same
Yeah,
thing,
ma'am.
just going through this loop and running it and trying it out. That's it. Okay.
Okay, ma'am. Now next will come 3. Is it so, no, ma'am? Next will come 3 and then we will proceed. Because not visited is 3 with minimum distance 10.
Sorry, for you, I mean, the next loop of you is what you're talking about? Next
In
loop
this,
of you, right? You,
yeah,
correct? I mean,
yeah.
yeah. So what will be next D is what you're asking. Yeah. So we've already said that this is actually, no, this will be 10 and 12, right? Yeah. So it will be 10, correct?
Okay, correct. Okay, ma'am. Let us proceed. We will do it. No problem.
Okay, yeah. We can just do
Okay,
that.
thank you, ma'am. Very nice, ma'am. Clear.
Yeah.
No.
Okay. I'll just run this and show you. Okay, this code.
Yeah,
This
yeah,
is
yeah,
the
yeah.
same
Please,
graph which we have. This is the
please.
same edges we have. So if we just execute it, just forget about whatever
Yeah,
clutter
yeah.
is there on the other side. I'll just clean it up 1 second. Just give me a second.
Manipulate some data so that we can understand
No, it's
how.
actually the same. It's actually the same set of vertices. Okay, this is the same graph which I have shown in this one. No, the same set of
Okay.
edges.
Yeah, yeah, yeah,
Sorry,
yeah.
same set of this thing only. I have put in this code also. So if you just execute it, I'm just showing you the distance which is computed. Say from 0, it is 0. So this is the dictionary of the distance, as I told you, right? So this is from source is 0. So 0 to 0, it is 0 only. 0 to 1, it is 3. That is what we have computed here. See, this 3, right? 0 to 1,
Yeah.
correct? And from 0 to 2, it is 2. That is what we know.
This is dictionary, ma'am. This dictionary represents a
Distance.
dictionary of.
This is what we are returning. No, this one.
Okay,
This is
written
what it is
distance.
displaying. Yeah.
Yeah, yeah.
And the code I will show you. See, it is returning distance, and that is
Yeah,
what it
yeah.
is printing.
Yeah. Distance is a dictionary. Yeah, yeah. Okay.
Okay. So this is the rest of the vertices 4 and 5. You can just figure it out. It's not difficult at all. Just hand running through this code, you will be able to do this. Okay. And this is exactly the same code. Whatever is there in our that PDSA GitHub page is there, no, which is open for all, so that you can just check. Okay. So one thing I have done here is because I looked at so this is
One
working.
question here, ma'am.
Yeah.
This distance dictionary is out of the source 0. When we started from this 0, if we have started, we would have been started from 3 or 4 like that. Source. We change it. Then dictionary will change.
Yeah, definitely it will change.
Okay. Ma'am. Got it.
Definitely it will
Got
change.
it.
See,
Okay.
first example, simply check the distance from 3 to 5, no?
Okay.
3 to 5, it will be simply 6. Whereas if you calculate from 0, it will be a totally different distance, right?
We can get a maximum 5 number of dictionaries out of this. We start from, right? Is it so, no?
6, no? 6.
Yeah, 6.
There are 6
We will
nodes,
get 6. Yeah. Okay. Thank you.
That's it. Okay. So the other thing I wanted to tell you was, so this is a directed graph which I have shown here. To make it undirected graph, I have actually added this other direction also. So the other method which I showed in this one is to make the undirected graph, right? You can actually, just 1 second. See, this is one technique which I told, we explained, right? Instead of the D edges, you add the other direction also. So if there is 0, 1, okay. So what I said is, like, if you have 0, 1, 10, then we can add 1, 0, 10. What I did in this code is, instead of adding the edges, I've just edited it in that matrix here, as you can see. I've just added, for if there is an ij0, then I put ji0 also as 1. And for ij1, whatever I put the weight, for ji1 also I put the same weight. This is just converting into an undirected graph. Okay. So this is just
it will double.
Yeah, you have this. It's a symmetric matrix, right?
Symmetric. Yeah.
Yeah, just to make it symmetric. That's it. Okay.
Got it.
Okay. So yeah, so that's about the Dijkstra's non-negative edges. Okay. Now I want to ask you one question. I told you when I started off and said that it doesn't work for. Let me just erase this. Okay, otherwise. Just erase it. Yeah, I said that it doesn't work for negative edge weights. Can you tell me why?
Because minimum will change now, ma'am. When
No,
it will
minimum.
go,
Yeah.
when we will pass through a negative path, then the minimum will change.
Can you give me an example where it doesn't work? It will not work. Simple. Say
Suppose
one
simple.
something like this.
Yeah.
Can anybody give me an example? Yeah, you can also try, sir. Yeah. So
You.
here you have say 1, 2, and 3. Say I have 8, 6, and
Minus 3.
minus 3. Let's see. Yeah. Then what happens? Minus 3.
Minus 3. 2
Yeah.
to 3 is minus 3.
Okay. What happens now? Source is 1. Okay. This is the source.
Source is 1.
Yeah.
Then 1 to 2 is 8. And 1
So
to
2, the distance is 8, right? 1,
8,
the
8.
distance of 2 is 8.
Is 8.
Correct? Yeah. Distance of 3 is
6.
6, right? But once you find whichever is the minimum distance, say this one, right? You have found this one, right? Now you convert the
Yeah.
visited as true, right? This visited, you make it as true, correct?
Yeah.
Because this is the minimum, right? So for the minimum one, whenever we are going inside, we are making it as, see, we have taken the minimum, and whatever are the minimum, we have made it as true, right? So this we make
True.
it as true. But if you see, there is a path like this, right? Which is of weight what? See, the earlier
5.
distance
5.
of 5. Are you able to
5.
see that? Yeah.
Yeah,
So
5.
there is a path of 5, but it does not identify that. It will actually take 6 and it does not visit that vertex anymore. Do you get why of Dijkstra does not work for graphs with negative weights? This is a counterexample. What Vyavut sir gave is a counterexample. Where the Dijkstra's does not work for graphs with negative weights.
Clear, ma'am.
Got it, right?
Yes. Yeah, ma'am. Thank you.
Yeah. So I have this is same example where instead of this vertex being 1, right? So I have this vertex being minus 5, right? So ideally, what should have been this the distance of 1? Can you tell me what should have been distance of 1?
Four.
Should have been minus 3.
Minus 3, right? Because see, this is the shorter path. This is one path, but this is the shorter path.
Minus
But
3.
after computing, distance of 1 will still remain 4 because we may not visit. Okay, so in this case, maybe so this is what we will
In this case,
freeze.
he'll rectify.
In this
because
case, it will correct. It will correct. Yeah.
Correct.
In the
Yeah.
case of 2, it will not correct. In the case of what is distance of 2? What will be distance of 2?
Minus 1.
Virus for
It should actually be minus 1, right? But because this is you can just hand run it with this example, and you will see that this is already set to true by the time this edge is processed. So we are not going to visit this vertex anymore. I mean, we are not processing this edge as it. Before that, this is actually visited is set to true, and hence this distance will remain 2 even though there is a shorter path of length minus 1. Okay, so I just change that in the code and then show you. This is the one. Minus 5. So what we are expecting here is for 2 we should have gotten a minus 1, and for 1 we should get a 1 we should get minus 3, correct? And for 2 we should get minus 1, correct? This is what we are expecting. The others should remain the same, I guess. Okay. Are you able to understand what I just said?
Yes, ma'am.
Yeah. So in this graph, we should get distance of 1 equal to minus 3 and distance of 2 equal to minus 1. But if you execute this, you will see that see, for 1 it is updated as we just mentioned, right? Because the minimum path is to 2. So this is what gets visited equal to true first. This path does not get set to true. That's why this path will actually get corrected and this will get to -3. Whereas this was set to true and hence we do not process it. So whatever is the earlier value, which is 2, will remain as the value. So you can see that here. For 1, you're actually getting it as -3, and for 2, you're getting it as.
This is not clear. What did you tell me?
No, I'm
How it
saying
is?
the same thing only. Same thing I'm trying to tell you. See, this path gets updated to -3, correct?
Yeah.
This path should have gotten updated to -1 because this is a shorter path, right? 4 plus
Yeah.
-5 is -1. But it does not get updated because when we processed 2 first, right? Here when we processed 2 first, and when we took 2, 4, infinity, infinity, etc., right? So when we took 2, the moment we set visited of 2 equal to true. So the next iteration, we are not going to process 2 anymore. I told you, right? Once we process whatever are these vertices which are processed here, right? This one, we will not process anymore. I told you, right? So for the same reason, once this 2 is set to 2, this is set to true and this part is processed. So it does not get updated with the -1. You can just try again, I'd request you to do the same hand running, whatever we did with the 1 to 1. You can do it with 1 to -5 and then you will understand what I'm trying to say. Okay. Just one loop you try to, two loops you just try to execute and then you will realize why the 2 does not get updated. Okay. So as you can see in the code, this is what I'm trying to say. This is the dictionary. So from 0 to 0, distance is 0. From node 1, distance is -3, which is correct. Here the node 1 -3 is correct, no? For 2,
Yeah.
it should have been -1, but we are getting 2 only. Got it? So this is wrong. What I'm trying to say is the Dijkstra's does not work for graphs with negative weights. We have given one edge with negative weight here, the -5. Hence, it does not give a
Okay.
correct output. Okay.
We are just checking here because
Correct.
this is
Yeah,
not
earlier it
working
was
for negative.
correct. Earlier it was 1. I just changed it to demonstrate it that it does
Yeah.
work.
Yeah.
Okay.
Yeah.
So yeah, so that's the Dijkstra's. Let me see. Okay. So Dijkstra's, everybody's clear, right? You can just do one hand running on your own and then you will understand what is happening. See, the adjacency lists are equally okay. Like there won't be any difficulty processing it. If you have any issues, please let me know in the next session. Okay. It's the same logic. So nothing more, much to worry about. And yeah. So the complexity, can somebody we have seen so much of this thing related to complexity. Can someone tell me why it is O of n squared?
We are
So
using
2 times
follow.
iteration is being done 2 times. One ON and two iterations are there for every
Infinity
node.
itself, you are doing n square map in infinity. That
Setting the infinity, right?
right.
This
Is n.
statement itself.
This is order of n.
No, this may not be order of n.
Yeah.
I don't think it's order of n, but
It's going.
no,
It's
why
n
would this
square.
be? Sorry, this is a simple computation, right? Oh, so you mean max of calculating max, is it? That's what is going to take time, is what you mean?
Right. Right, ma'am.
See, we don't know how the NumPy is doing it for us, no? So for now, let us just assume it is some constant
Yeah,
time thing.
confusion in number. We don't
But
know
even
the numpy
otherwise,
concept.
even otherwise, you can see this, right? You have one for loop, which is like number
And we
of
have 2
rows.
for loops, right?
Yeah,
Two
this
for
is one
loop.
loop.
Yeah.
Yeah, this is one for loop, and here it is O of n. Okay, this is O of n, right? Because it's all 4 in range, right? This is 4 of n, and you have another O of n here, right? So this is one O of n outside, and this plus this inside, correct? So it will be O of n square. Okay. So yes, NumPy, I am not saying it is done in constant
Because
time,
we have
just
taken
trying to analyze it. Yeah, sorry. Yeah,
we have taken O of n because ma'am this is iterating through rows.
correct.
Both is it so no? Okay.
Yeah, rows and this is columns because this is square matrix, right? We're giving size comma size, no?
Yeah.
Here we have given size comma size square matrix, so it's
Hmm.
a n by n. Okay.
Okay, ma'am. Okay. Thank you.
So that is for the Dijkstra. For this adjacency list also, there is something slightly better. I think it is O of
That is also for the O n square.
M, I think.
No. N
Sorry,
is
O
O n square.
O n squared, but if M is much smaller, see here it will definitely go through the both four loops, right? This 4 and this 4 is definitely O of n. You cannot escape that. But in adjacency list, I think you can actually look at it as O of m. If m is much smaller than n squared, right? So this will be a better.
Ma'am, M into N, right? M
It's not
adjacent.
m into n.
If
It
M
is
are
n
the
plus.
edges, I'm talking about this inner.
In the lecture,
Is it mn?
ma'am, I think it is
One
n
time we
square.
have to run through all the vertices, right, for the very first time. And for the inner for loop, we are doing for the edges in Dijkstra.
Correct. So this one for V in W list, right? This one VD
Yeah,
for all the
this is for
edges.
edges, all the
Yeah.
edges. So N into
Again,
N.
So this is O of not. Okay. O of n into O of m is what you're saying.
Into
No,
M.
but that is.
N
Oh,
will be for all vertices, right? This ninth line is running for all
this is O
vertices.
of mn, is it? That's what you
Yeah,
mean?
yeah.
Hello.
But then that won't be n squared, no?
Hello.
Oh,
Mm,
okay.
The for loop
yeah,
for
that
the
won't
for
be n
loop.
M
squared.
is the
Let me just see sir's.
not
It'll
N
be n
square,
squared also.
not
Sorry?
N
It'll be
square.
n into n minus 1, man.
N
So it'll
into
it
be
is
n
One
n
squared
square,
second.
also.
ma'am. In the lecture, it is n square, ma'am. Both are
M is
Yeah, so I'm just.
order
n
of n
minus
square.
1 only.
Which one?
M is n minus 1.
This
yes.
one.
Yeah, so n
N
into
square.
n minus 1 will be n squared only.
Sir
Yeah.
said the for loop it will be O of M, but for max of W mat it will be n square. So he calculated at n square.
Okay, so m is at
Yes.
most n minus
For
1 is
for
what you're
the
saying.
for the
Is
for
that what
loop,
you mean?
yes.
Yes.
That's why the O of n squared comes. Okay.
Yeah.
Okay, maybe I have not looked at it properly. I'll just check and later. Yeah, that should be correct.
Okay, ma'am. Proceed, ma'am. No problem. We will see in the lecture.
Yeah, okay. Sure. So now we have the Bellman-Ford algorithm. Okay. So I have just shown you that the Dijkstra's does not work for graphs with negative weights, but we have an algorithm which works for non graphs with it works for non-negative edges as well as it works for negative edges. But what it does not work for is graphs with negative cycle. So I have to actually distinguish between the three, right? So suppose you have something like this, say 8, 2, and minus 1. Is this a negative cycle? Let me just put it like this. Is this a negative cycle? Do you call this
No,
a
man.
negative cycle?
No,
Negative weight cycle, sir. No?
no,
Why?
it's not negative cycle because the sum of the weights is not negative.
Correct. So when you say the weight of a cycle, what it means is the sum of the weights of the edges contributing the cycle. Okay. So this will be like 5, right? Whereas if you look at something like this, okay.
9, no, ma'am. It is 9, no?
Oh, sorry.
The weight of the cycle here is
It's
Oh,
9.
sorry.
9.
Yeah. Sorry.
okay, no problem.
Very poor at basic arithmetic. Sorry.
No, ma'am. Just we are understanding or not. We are just learning.
No problem. But
Together,
this is what is the weight of this cycle? Can you tell me?
this is negative cycle, -1.
This is minus 1. Now tell me, why does it not make sense to find the shortest path in this one? In this graph. Say for instance, you have some other node which is coming from here and there is some other. So this is your say source node, okay? It's, source node and this is the destination. Why does it not make sense to compute the shortest path from S to D. So here it is say 10 and here it is say 11. Can someone tell me?
Yeah, I think Deep has mentioned in the chat.
Okay, I'm not seeing the chat. But yeah, can you
So
speak?
basically, if you recycle it, I mean, you keep going around in that
Correct, correct.
cycle,
Yeah.
you'll keep reducing the weight.
Correct,
So
correct. Because the overall weight is -1. Every time you travel this, you incur a weight of -1, right? So you start off with 10 here, you come here, okay, you have traveled a distance of 10. One time you go through the loop, you incur a weight of -1. Next time you go through the loop, you incur a weight of -1. Because -1 is the total sum of this cycle, right? Correct, no? So every time you go through this, it will keep on reducing. So does it even make sense to compute the shortest path in such a case? That's not what we want, right? We want something more realistic, more logical, right? Is it correct?
But
Does
ma'am,
everyone? Yeah.
just out of this thing, I mean, considering that we are keeping a dictionary called visited, would that repetitive action happen?
No, no. See, visited is when you are actually setting it for minus. Or 1 second. So Bellman food, I'm not sure. I don't think it's keeping a dictionary for.
No, it's not keeping a dictionary,
Yeah,
ma'am.
it's
So,
not keeping. So
yeah,
maybe you can try with a dictionary. But
yeah,
even then, I'm not sure because see, even logically speaking, right? I
yeah,
mean, algorithmically, I understand what you're trying to say is I'll just go one loop.
yeah, right, ma'am.
So why should you even go one loop, right? So if you come like this, say for instance, you just come like this, right?
Yeah,
It is much lesser, no? This is like -9 or something, right? 10
mm,
plus -9 plus 11 is what you're getting, right?
yeah, yeah,
If you had just gone through one loop, then you would have gotten a higher weight, right? So it's not even logical to think about a shortest path that way. That's what algorithmically you can set restrictions. Say I'm saying okay, I'm going to go through this cycle just once, or I'm going to say I'm not going to take the cycle at all. But again, it depends on the direction also. See, suppose the direction was something like this, no?
yeah, yeah,
Then you cannot say, okay, I'm going to skip the cycle and coming this way. That doesn't make sense.
yeah,
So, I mean,
right.
if you probably going through the cycle would have made sense because you're going to go through some edge of weight 11 and all that, right? So, those kind of combinations kind of may not really work. You're getting the point what I'm saying, right?
Yeah,
Depends
yes,
on the
ma'am.
directions you have to see. I mean, yeah, those things you will have to take care of. That just doesn't make sense that
Okay, okay, ma'am.
logically. Okay. You can do that possibly algorithmically if you're very clear about the structure of the graph and you know that I'm not going to have any clockwise cycles and then I'm going to travel. So, I mean, some such restrictions you have, some such, you are sure about the structure of the graph, right? Then you can possibly do a lot of fine tuning. But in any general graph, any simple general directed graph, it probably doesn't make sense to compute the weight when there is a negative weighted cycle. Okay.
Okay, ma'am. Yeah,
and
thank you, ma'am.
I think another thing, ma'am, because in the Bellman Ford, you keep updating all the vertices. That's the primary assumption, I think. And it is
Yeah, we
not like
keep it's
the
no, it's not at
Dijkstra
all like
where
the
they have,
extra. It is simply you
where,
keep on doing it. Yeah.
you don't have burnt depots, so you don't revisit those burnt depots. Here you are revisiting those depots
Everything
and
you
keep
keep
updating.
revisiting.
Yeah.
Yes. No, but what she
So you
suggested was
may so so this
yeah.
is a simple graph, but you may have a graph where there are other nodes connecting to it. You'll keep updating that, so that negative will keep in a cycle will keep running into a loop.
Correct,
I mean,
correct.
it'll
So
be
no,
very
what she
difficult.
suggested is possibly why what if we had a visited? Like can we do something by having a visited so that we ensure that we visit this negative cycle only
Uh,
once? Get some
right,
improvisation for the Bellman code. That's possibly what she was referring to. Or at least that's what I understood. Like why can't we do that? Right? Because we are not
right,
doing that is why it could go to a negative. You can keep on visiting the vertices. It's just a blind process, right? You keep on doing it until you yeah kind of stabilize, right? So but here it
right,
is not happening. Yeah.
right.
Ma'am,
So
one thing.
yeah.
In Calvin Ford, we do not do infinitely. We do it n minus one times. We do n minus one times because to consider the longest path, right?
Yeah.
That is the thing. So this
No,
negative
no. What
cycle,
is the longest part? Sorry.
the n minus edges has to be covered for the longest, for the farthest vertex. I can
That's
say.
correct. Yeah.
Yeah. So that is the thing. It will not occur infinitely, but
Okay.
it will occur many times, and this is not the thing that we have to compute, right?
No, no. See, it clearly does it only for n times, right? Because that's our fourth
Yeah,
loop
n
here.
times we are taking here n times, just
Yeah.
like that only. But if you do for n minus one time also, it will work, right? Sir even told us, na?
Yeah. Sir has said that it can
Yeah.
work for n minus one times as well.
Yeah, if you do for n minus one time, it will work because the maximum number of edges to connect any vortex, the furthest vortex, is n minus one edges we require, right? That is
Okay.
the thing.
Ma'am,
So
basically we run the loop n times because we take for I in range of rows. But had we done it for n minus one times also, it would work because we have only n minus one
n
edges.
minus one edges to connect the farthest
No,
node.
no. So let me just ask you, what is the point that you're trying to say? I did
Yeah,
not
the
get the.
point is that this
Yeah.
negative cycle will
Uh,
not go infinitely.
no, no. It's okay. So probably infinitely was a wrong thing. What I
Yeah,
meant
n
was
minus
by,
one time it may
see,
go, and there is
yeah,
no point in
yeah. So
doing
the
n
n
minus.
minus one time it would be going through the same cycle, right?
Yeah, yeah,
That's
yes.
possible, no?
Yeah, it will be going for n minus one time, and it doesn't
Yeah.
make sense of
Correct.
calculating
Exactly.
the,
Correct.
yeah,
Got it.
the
Yeah.
distance or
Yeah. Now I get what you're trying to say. Got it.
yeah.
Yeah. Yeah, I got it. So yeah, it's not an infinite loop or anything. It will only execute for so many times. But yes, uh, I mean it's not the n minus one that we want, right?
Yes.
It's not the set of n minus one that we want. Yeah. So this
And
algorithm,
this
if
is,
you have understood,
ma'am,
yeah, sorry, yeah,
this is only for the negative cycle only. If it is a positive cycle, that doesn't matter. It will work fine, right?
Yes, yes.
even negative edges it will work. Only thing the cycle should not have negative weight. In the
Okay.
sense that I showed you two differences, right? It might have a negative edge, that is okay. But the
Yeah.
overall weight of that cycle should not, sorry, overall weight of that edge should not be, sorry, the cycle should not be negative.
Okay. This is the only condition when it will fail, right?
Correct. Okay. So
Okay.
what, see, so the algorithm in textbooks, if you see, what they will do is, you'll execute it for n times, and then you will run it once more, and for any edge, if this distance, right, the new distance that you're computing is actually reducing, the new distance, the sum plus the current distance that you're computing is smaller than the current distance that you've computed, even though you have gone through it n times. That means that there is a negative cycle somewhere, and the the Bellman-Ford algorithm will report it as a negative weighted cycle. So I will just show you what I'm talking about.
Okay. Okay.
See, in this case, okay, this is so Bellman-Ford algorithm is pretty. Okay, before that, I should explain what the algorithm is. It's very straightforward. If you have understood what the Dijkstra's does, right? This is the only step which is involving. Otherwise, it's just blindly going through the matrix, right? I mean, it's just going through this whole thing again and again and again until so many times. And the argument, right? By the time it finishes, there is this proof of correctness which you can come up with. It says that what you have found is the minimum distance between every possible, sorry, the source to the every other vertex. This
We
is
have
very
not discussed
simple
here
system.
this loop, man. We have not discussed this loop, no?
No, no, there is nothing in this. This is what I'm saying. So it's actually sub of what we looked in the Dijkstra's, right? If you have understood this part. Sorry,
Okay.
where is that Dijkstra's? I'll just show you. This step of Dijkstra, right? This step of Dijkstra, it's not even
Yeah.
checking the not visited. This step of Dijkstra plus this one. This is all what it is taking, and it is running it in 3-4 loops. That's all what it is doing. I'll just show you the code now, then you will understand. See, that step where we are checking whether there is an edge and then updating it.
Hmm.
That you are simply running it in 3-4 loops. So the intuition is by the time you do it for n times, if there is no negative weighted cycle, you would have found a path which is of length say n minus 1, and which is the longest path which is possible in any graph. Got it? You cannot find a graph which is of length more than n minus 1. So, but if you do the iteration for say n minus one, sorry, the n times like the three times the three four loops, right? You would have found that is the intuition behind it.
Okay, ma'am.
Is it
Okay, fine.
confusing?
No, no, ma'am. Okay, fine.
Okay, so is it okay for everyone? This is there is no
Yes,
condition
ma'am.
checking. Only thing is whether there exists an edge. That is all what it is checking, and then you just keep updating, updating, updating. That's it. Because the negative edge could be coming from anywhere, so you are, I mean, it could be coming from the same edge that you, sorry, the parent that you visited, so you again check with the parent whether the distance is correct. So in the previous case, as I said, when I said the 0 and 1 is done, no, then I drew a line around the 0 and 1, said that it is done, right? But here that is not the case. It will again go and check for 0 whether it is correct. It will again go and check for 2 whether it is correct. It will again go and check for 3 whether it is correct. So you keep on checking everything, and you keep on checking, and why it finds the minimum path in n loops is, sorry, n iterations, is because the longest path that you can find is of length at most n minus 1. Got it, no? Okay, you can just yeah, try it out once. If it's not working, let me know. Okay, very simple, very straightforward. There is no thinking process written. I mean, even handwriting is not required actually, if you just sit and think about it for a while. Okay. Okay, I just wanted to show you the scenario where, you know, it kind of checks whether there is a negative weight cycle. That example I wanted to show. So this code, whatever is there, right? This is the exact code that is there. These are the lines which I have just written just to check the negative cycle that I'll explain to you. So first, let us see the. um just going to- so this is for. Oh no, this is negative. Just take- This is without any non-negative edges, so we should get the same as the Dijkstra's. Okay, hopefully. Hmm, sorry. Shouldn't be 15. Just give me a second. 014 022 014 022 121. So this one 125 228. Okay, yeah. So Bellman Ford, what we are looking at is, so Dijkstra's, whatever we saw was an undirected graph. For Bellman Ford, we are looking at directed graph. Can you tell me why? Does it make sense to look at undirected graph in Bellman Ford?
Because of the negative weights.
Sorry?
Because of the negative weights.
No, negative weights need not be there, no? It works for non-negative weights also, right?
No, the direction matters when there is a negative weight, no?
The cycle, is it to do with the cycle? Because
No, no, okay. So
it
let me
doesn't
just
work for
ask
a.
you, for an undirected graph, Bellman Ford works or not?
Yes, it will work well.
Non-negative weights, non-negative weights, that's the basic
Yeah.
case, no? Non-negative weights. Um,
Extra is the
undirected
special case of Kelvin 4.
Correct. That's just a special case of Bellman. Okay. Now, does it work for uh, undirected graph with negative weights?
It will work. It will work, ma'am.
It will work. Why?
Because there will be no cycles in the undirected graph. There will be no negative cycles in the undirected graph, no?
So one second.
No, ma'am, because it will be again the case of negative cycle. I think.
Yeah, that's what. So negative cycle need not come because both sides it will have the same weight, right?
If negative weights are there, there should not be. Then it should be directed, not undirected.
No, but this is the equivalent direct undirected graph, right? So both sides, if you have, this is both -5, So there is no negative cycle as such, right?
It's a negative cycle, no, ma'am. -5,
This is,
-5,
actually,
-10.
Bellman port will not work for the
No, no,
negative cycle only.
no. This is not negative weighted cycle. No, the weight here is zero, right? It is not
Yeah.
negative weighted cycle. No.
So it will work.
What if you had another one here? Say, so this is 6, and you had
I'm
somewhere
not sure,
close.
but I think
This is a negative weighted cycle, but
we are not able to think up to that level, whether it will work or not, because we
yeah,
are just learning. Without running the Bellman port 2 or 3, 4 times, we
yeah,
will not
yeah.
have control over the running, how it is running. This is the problem, ma'am. That's why
No,
we
no,
are not.
no. You don't have to. No, see, Bellman for running, you don't have to worry about it. What you just have to think is like whether there can be negative weighted cycle when you have an undirected version which has negative weights. See, undirected graph with negative weights. Is it possible that it will have a negative weighted cycle? That's all what you have to worry about. I'm not talking about nothing specific to Bellman Ford. Bellman Ford finds it for graphs without negative cycles is clear, right? For
Yeah,
graphs with negative cycles, it may not correctly find it. That is also, I mean, it'll actually return something false and say, I mean, that's what we are coming to. But yeah, so in this case, yeah, I'm a little confused now. Let me just check and get back to you. Okay, so undirected graph, negative weights. Okay, let me check and I'll get back to you. Okay. So for now, we are looking at the directed graph, okay, with negative weight. So here, will it work? In this example, will it work?
Yes, ma'am.
Okay. There is no
yeah, it
cycle
will work
here.
because
No, there is no.
there is no negative cycle.
No, there is no cycle at all in this case, right?
Yeah,
Like
there
there
is
is no.
no cycle at all. It will work.
Yeah. What if the edge was like this? No, this edge cannot change. Okay, let me put it something like this. What if the edge was like this? 5. Then I put something like this. Okay, so this is a negative cycle, right? The one, this one.
Yes.
So in this
Now it
case,
is
it will not work, right? In this case, it will not work. Right?
it
I
will not
had
work.
written some example. Let me just see. It's the same
It
example.
will work, but it won't
Let us
give the
let us
desired result, I think.
Yeah,
let us
it will work. It
iterate
will work, correct,
one.
but it will
Let
not
us
give the correct
iterate.
output. So we cannot
Yeah.
say it works. Okay. Working means correctly working. Implied. Yeah. So what was I saying? Yeah. Mm, so for non-negative weights, it should have worked, but let us see. Let us see if this is correct. So you have 0, 0, 0 is correct. From 1 to 4, is it correct with this one? Sorry, 0 to 1, it is 4. Yeah, there's only one direction. So here you can see this path does not exist, So this is the correct one. 4 is the distance, which is correct. Because there is no, this is the directed graph, right? So this path does not exist. In the diastress, we saw that this should have been -3. But here it is not there because only this path exists. This path does not exist, right? Okay, so this 4, but distance to 1 being 4 is correct. Distance to 2 being 2, that is also correct because no, that is not correct. Mm, okay, so this weight was 1. I'm just checking. Okay, sorry. Okay, the example I have given is this 1 is what I have given here. Okay, this one 1 to 1. This is what we have run now. Okay, so 0 to 1 is 4. That is clear. 0 to 2 is 2. That is clear. Then 0 to 3. Yeah. So for non-negative weights, it works. You can just assume it that it works. And I'm assuming this dictionary output is also correct. Okay. If you find something wrong, just let me know. Now negative, this thing with no negative cycle. So instead of this 1, I have put this graph. So here it is -5. So this should work ideally, right? Let us try. Just copy paste it there. Okay, 0 is correct. 0 to 1, 4 is correct. 0 to 2 minus 1. Yeah. So it has found this part. That is why it is set to -1. This one. Okay. To 3, it has seen 7. That is from, so
One,
0, 1,
1, 2, and
2.
3. Yeah.
So this will be a weight 7. Correct?
Right.
0 to 1 is 4. This is -5. This is minus 8. Sorry, this is 8. So 8 plus 4, 11 minus 5. Sorry, 8 plus 4, 12 minus 5, 7. Okay, now 4 is again -1 plus 10. Correct? That is the 9. Okay. Now the other path is also, this is also 10, right? So it's the same thing. -1 plus 8 plus 2, that is also 9 will be correct. So 5 is from so there should be another part, right? So this is -1. Yeah, this part. -1 plus 8 plus 6, which is 30. Okay. So this is okay, right? With negative weights it works, whereas in the case of diextras we saw that with this will not work. Okay, is this correct?
Yes, ma'am.
Okay. Now we will see the case which I was talking about. How will you find out what if there is a negative cycle? So I have changed two things here. One is this edge, I have changed the weight. The other one I have changed the direction. Sorry, 1 second. So that one was also. No, this is weight I have changed. I'll just show you. You see if I have a figure for that. Yeah, I have a figure. This is the figure I have. Okay. So here, as you can see, we have a negative weighted cycle, which is -5 plus -1 plus 5 is -1, right? This is a negative weighted cycle, correct?
Yes, ma'am.
Right, yeah. Okay. So this will not work is our assumption, right? This should not work. It will give wrong answer, I think.
You are telling me it may not work. What does it mean? It may work also.
It may work also. Correct. It
may work.
may work also. Yeah, it may work, but it's not for sure.
Okay.
And for negative cycle, we cannot, right? Because anyway, it will be working for this cycle will be going for n-1 times. We will not get the correct
Oh, so
output
you're
at all.
saying, okay. So you're saying for sure it will go through this n-1, is it?
Yeah.
No, in this example it might, but can you tell me, like, for every negative weighted cycle, it will not give the correct answer? Is that so? For
Okay,
every
ma'am.
negative weighted
I'll see the example
yeah,
if I
we
can.
have to, yeah. So,
Because
so
anyway, if we are having any negative cycle, it will go n-1 time. It will not stop. That's what I want to say.
Right,
The
right.
previous
Correct.
vortex
Got it.
previous vortex will change, right? Every time. Here we are changing the vortex distance.
Correct. Got it. Yeah.
Yeah.
So
Just
yeah,
check.
ideally for every negative weighted cycle, it will not give the right answer, right? But yeah, let us just check it offline also. If there is an example
Yes.
somewhere we can. But yeah, if you look at the proof, it looks like it will actually be, caught in that negative cycle, and once it is n-1 is over, it will come out, right? That's the idea.
Yes.
Okay. Yeah. Okay. So now what are we going to do is we will just check once again, right? So what does this loop do is, so you are just going to run through every edge once again. Every edge in the sense that for every edge you are going to check whether, if I compute the distance once again, right, this new distance, which is the current distance plus the new weight. New weight is, this is the negative weight. Okay. I'm checking it for every edge. So you can just assume that this is for the negative edge which I'm going to explain. It will check for positive weights, everything. But for the negative weights, this will make a difference because even after we have completed n iterations, the next time we try it, it will still, this value will still be less, which should not be. The calculated current distance should be the smallest once all the n iterations are completed. But if we do just one more iteration, then we find that the distance will still get reduced. See, what we are doing is we are checking min of distance of v, comma, that distance plus the weight, right? That's what we are checking there. Here, you are actually comparing the newly computed distance with the existing distance. This is the existing distance of that vertex. And you're newly computing the distance to the another vertex where the UV weight, right? This is negative. And this means that this value will be smaller than what was the pre-computed value, which should not happen. For Bellman-Ford, for after n iterations, it should stabilize and it should not reduce any further. So this will try just once again and it will print false if there is at least one such edge where this condition is satisfied.
And does it stabilize after n minus 1 iterations or n iterations?
It should after n minus 1, right? Because you are actually looking through the edges and there can only be at most n minus 1 edges. No?
Right.
Ma'am, I'm not getting this because in 19th line you are checking the distance of V is greater than
Distance of V is the current distance.
current distance. So
And the
we-
newly
that is
computed
what,
distance is still smaller.
yeah, that is what we are doing in 15th line. We are taking the min of it, right?
Huh.
Yeah.
No, so what I'm saying is after n iterations are over, it means that you're done with the graph.
Yes, we are
But
done
if it's
with
still
it.
reducing, it means that there is something wrong.
Okay.
If you had all negative, non-negative weights, it will not reduce.
It will
Correct?
not reduce. Correct.
Because you are actually adding it once more.
Yeah. Yes. Now
But
I
if
got it.
because it's a negative value, it is actually reducing. The
Yeah.
computed value, which should have been the correct shortest path distance, is still reducing as compared to the earlier computed value.
Okay,
Which
then it
means
will
that
increase.
something is wrong. Yeah, there is a
There is
negative
a negative cycle. Yes, got it. It is a very impractical case, right, ma'am? If we have negative cycle, see, every time we are going somewhere and we are traveling,
So
but
what
we
you
are
mean is
getting.
there is no practical, I mean, real life scenario where this can happen is what you mean?
Yes, I think that
Yeah,
because
no, I'm really
very
not sure
impractical.
because see, there are so many, see, in biology, in chemistry, and all that, these exothermic, endothermic reactions and all that. No? So you can add the weight of these, what is energy released or energy consumed or whatever, right? We have no idea what kind of combinations can happen. People who are from chemistry can possibly throw some light. And biological sequencing and all these things, right? There are so many dependencies which are kind of, we have no idea about. So we cannot, blanket conclude that, such a thing will not happen. Yeah. Okay. So, but it doesn't make sense to compute the shortest path is what I'm saying. Like there could be directed graphs like that, but there is no point computing a shortest path in such a thing.
Yeah, this can be the case. Yeah.
Okay. So is this okay for everyone? This last condition?
Yes.
Yes.
Okay. Does anyone have doubt on this? Okay. So I will just try executing. So what I have done here is, these are my edges. Let me see. I hope these are the edges.
So Wellman-Ford can be used to check the negative cycles also.
Yes, Bellman-Ford can actually be. So if you see the standard algorithmic textbooks, right, you will have this condition last.
Okay.
If it is entering a negative cycle, then it will say that whatever it has computed may not be correct. That's why it's returning a false.
Okay.
If it does not have a negative cycle, then it will return the dictionary.
Okay.
So I'm hoping this is a correct one. 0, 2, 2, 1, 2, 5, minus 5, 3, 1. 3, 1. Yeah, and this direction is 5. 2, 3 minus 1. Yeah, 2, 4, 10. 4, 5, 5. Yeah, I guess it's okay. Yeah. So this is the graph that we have, and ideally it should not. It should give us a false, and I think it does. I mean, I ran it some time back. I just want to show you. Mm. Yeah, it does give false, but it gives between 1 and 2. Okay, so this distance keeps reducing. That's why. So if you go from here to here, right? So this is the first edge that is encountering, where the distance keeps reducing in the last iteration. It's going through all the edges, right? So it went to 1, 0, 1, it went to 0, 2, then it went to 1, 2, and there it sees that, okay, this can actually reduce in the next iteration, and it's reporting. That's why it's showing 1 and 2. I'm displaying the U and V here. This U and V, right? Which is causing the negative weight cycle. One edge which is causing the negative weight cycle. Okay. Okay, so that's it. I mean, this is one extra thing which is...
This U and V is giving, which is causing this negative cycle.
Yeah, one, see, there are, this cycle, full cycle contributes a negative weight cycle, right? But what
Yeah.
I've just displayed is one edge, the first edge, which is part of that negative weight cycle. That's it. So if you don't return false,
how
then
the loop will decide that this is the one edge? First, which edge it will? First edge means UV.
No. So say, how are we going through the edges? We are going from 0 to 5, then 0 to 5,
Okay,
right?
okay,
So 0,
okay. We
yeah,
started.
0, 0, 0, 1, 0, 2, 0, 3, etc. Then 1,
Yeah,
1,
yeah.
1, 2, 1, 3. So if you go by that, this will be the first one then. So
1
if
to
I
2,
do
1 to 2,
this,
yeah. First.
I don't know if it will print all the... It's still printing the dictionary, I guess. See,
0 to
only
1, 1 to 2, right.
Okay, maybe it's probably not the best way to do this, but I just wanted to give you this one heads up also, that if it is a negative weight cycle, then you can actually recognize it using this step. Okay. So
Okay.
yeah, so that is about Bellman-Ford also. So Floyd-Warshall is actually a little more intense in the sense that there is this transitive closure of matrices and all that. So if you are comfortable, we can do that. But I'll just give one brief idea about Floyd-Warshall and what spanning tree is, and algorithms I will explain in detail in the next session. Okay.
Before going, because we could not go to the lecture of the Floyd one.
Sorry, before?
We could not go through the lecture of the Floyd also. So we can start with the just interpreting the Floyd.
You want a Floyd-Warshall? You want to run it? Is what you're saying?
Yeah.
Yeah. That we can do. But I'm saying, like, today, let us not even look at the algorithm. We will just simply look at what the idea is, how this Floyd-Warshall algorithm came about.
That will be fine, ma'am. Yes.
Yeah. So actually, see this transitive closure of matrices, right? So that I'm not sure how many people have heard of it. I'll just show you one simple example. So consider this graph sometimes. I have graph like this. Okay, simple, so that you will understand it easily. Some simple example. Okay. Now I want to have the adjacency matrix of this. So 0, 1, 2, 0. It's a simple adjacency matrix. Okay, 0, 1 matrix, not the representation that we were looking at. So you don't have anything in the diagonal. In 0, 1 you have an edge. 0, 2 there is nothing. 1, 0 there is nothing. 1, 2 there is one edge. 2, 0 nothing. And 1 nothing. Right? So this is the matrix. Now, what does this mean by this matrix? I'm trying to interpret it in a certain different way. What I'm saying this is, see, this is the adjacency matrix, say A. Now, A power 1, I'm just saying I'm not multiplying, I'm going for matrix multiplication. So when I say A power 1, I'm just looking at A. Right? This matrix shows an entry of 1 if there is an edge between 0 and 1. More precisely, if there is a path of length 1 between 0 and 1. Okay. And from 1 to 2, there is a path of length 1 here as well. Right. Now suppose I take a power 2. What is a power 2? You are multiplying the two matrices. Going to take a into a, which is a square. Okay. So 0, right? This into this
Right.
is it's also 0.
1.
One second.
No, the second one will
This is
be
what?
0. The last one will be
0,
1.
right? Last one will be 1, right? This middle one is 1. Yeah. Okay. Now, this is again, I think this is 0. The first one is 0. Second one is again 0. Third one is also 0. This is anyway the last row is 0, right? So, 0.
0.
Now, can you interpret this one from what I told you earlier? Here, I told you if you consider this as a power 1, then there is a path of length 1 between node 0 and 1. Right? In a power 1, this 1 indicates that there is a path of length 1 from 0 to 1, and there is a path of length 1 from 1 to 2, this one. If you look at a squared, there is only 1, which means that there
That
is
is
a
0,
path of length 2.
0 to
There is
2.
there is a path of length 2 from 0 to 2, which is the case here. You can see this, no?
How it is path of length 2, ma'am?
No, this is the a squared, right? The power of a is what you have to look at. See here, a power 1. So whatever 1 entries are there, it is the path of length 1. The a power 1. The power of 1 is what I'm talking about. Sorry, power of a is what I'm talking about. I get 2, then it is a squared. If you put a3, there will be a 0 matrix. You can just try it out on your own. Okay. So a squared into a is what you have to try. It will be 0, 0.
So
It
the
is
power
0.
is the
How it
length.
is?
Power is the length, path of length. I mean the
Length
of the path.
Right.
Okay. Got it? No, transitive closure we call this.
Hello,
Okay,
So
ma'am.
in
power.
Floyd partial, sorry.
Suppose power. Suppose another matrix is there where the path is 4. Then how we will get this one? By example, where path is 4.
So matrix multiplication takes some time, no? So that's why, and you
Okay,
need to
okay.
have say 4x4 matrix, 5x5 matrix, and all that. So that's why I took the
Okay,
simple
okay.
example just to demonstrate.
Okay.
Because
Okay.
the number of nodes will increase the dimension of the matrix, and if you
Okay.
do a multiplication, right? So because it's square matrix, definitely multiplication is possible, and you can do that. Okay. So this is
The
just very basic idea what I'm trying.
power gives the length of the path, right?
Correct.
Okay.
What
And
is
this
the
end.
transitive closure out here, man? Why is it called transitive closure? What is the closure out here?
Sorry, closure matrix. No, I did not understand. Why we call it transitive closure, is it?
Yeah, you said this is the transitive closure, so I didn't actually understand the term. So what is the closure out here? So is it coming to the end
No.
of the matrix multiplication? Okay.
Can I say, ma'am?
So, yeah.
I've got an answer. Yeah.
Suppose you are going through the path in a graph, then that goes to the director graph, and you go directly from the first point, beginning point to the end point. That is a transitive closure. That's what we are going from 0 to 2. It is 1.
Yeah. So the next question I was about to ask is, what does a power n minus 1 give you?
Yeah. Okay.
A power n minus 1. So see, any path, right? It can be of utmost length a power n minus 1, right?
Right.
So you only have to execute this. Okay, so Floyd-Warshall basically makes use of this process in which you compute the how do I put it? So you have a node from say I to J, I and J, okay? And there is a path like this. There is another path which goes like this, okay? This actually you can capture in one of the intermediate matrices. Say some A, P or something, you can capture that there is this path from I to K and K to J, and then there is this path from A to J. Okay, I will show you the algorithm.
Ma'am,
I need to explain a little more. Yeah, tell me.
ma'am, if this is a undirected graph, will it work in that case also?
You have to have both the entries, both directions, right?
Yes.
Yeah, you will have entries in both directions. That's it.
Then also it will behave like similarly.
Uh,
Not similarly, but it will behave correctly. That is what I am trying to say.
yeah, it will behave. Only thing again, negative weights. I'm not sure. One second. Negative edge. Oh, it will not work with undirected graph and negative edge weights. Otherwise, it will work for both. Directed and undirected, it will work. If it is negative edge weight, it will not work. That's a problem.
Okay.
We have to we have to try some example and figure it out. Yeah, but I have not tried it out. But yeah, it should be clear. Okay, so I will come to this. So basically, this algorithm makes use of this transitive. So the transitive closure property of the adjacency matrix is what we take the intuition from, but in the algorithm we make modifications in how to do it to find the longest path. So what I was trying to tell you about the MI, so when do we stop this, right? When do we know that we have found all the shortest path? We just need to execute it for n minus 1 times, because we know that even if it's the longest path, we would have found it out. Got it? No? So that's what I meant by finding out the A power n minus 1. So in detail, I think we will go into the next session, because there is a few more things which I will have to explain. That B matrix is this one, right? This one. This is something that I have to explain. But it will take some time. So I guess we'll do it in the next session. Okay. So we have to do for 1 second. Do it for yeah. So yeah, these three we will do the next session. That's fine. Okay. Anyway, I won't be able to finish the Floyd module today, even if I start like late.
Right, ma'am.
Okay.
Next
Okay.
session
Any
is
other questions?
tomorrow, na, ma'am.
Tomorrow is some other session we have planned. So maybe Saturday, as usual, we will have. Sorry, Saturday we will have this session, and maybe the coding session we'll have on
For
Saturday.
me, tomorrow also there is a PDSS session. I don't know why.
Yeah, I know. There is a PDSA session for practice assignment solution. I think we have.
Okay.
The practice programming assignments, right? So if you're comfortable with that, you can just go ahead with it. I mean, you don't have to attend. Otherwise, it will be good to attend.
So
So one
it
more
will
thing
be
I
on
wanted
graphs
to tell
only.
you. One more thing I wanted to tell you. Sorry.
It will be on graphs only.
No. The whatever programming assignments that we have looked at, right? That one. Those programming. I'm not sure which week we are intending. Have you seen the calendar? Which week?
No, it is for me. It is fifth week, right? I don't know.
Yes,
It is
No,
not showing any
tomorrow
other
no week
details.
is mentioned. It
Yeah,
is
program.
general
Yeah,
program.
week is not mentioned. So I think Then I guess week 5 it should be.
Yeah. Okay.
I'm guessing it
So
should
it
be week
will be
5.
for graphs only. Okay.
One more thing I wanted to tell you. I mean, I was hoping you could just have a look at it. See, these trees are some very beautiful graphs. Okay, some specific with some very well defined and specific structure. So this without cycles, right? They do not have cycles. So any connected acyclic graph is a tree. So if there is a connected graph is a tree if and only if it does not have any cycles. Okay. So trees are like very beautiful. So a lot of hard problems which are there in simple graphs and other things, they generally have an efficient solution in the case of trees. So trees are like really well studied, and they have some very beautiful structure that you can understand, learn, and everything. So in the next topic, that is spanning tree, right? I just wanted to briefly mention what spanning tree is. So a spanning tree is, you have to have every vertex included. This spanning tree is a subgraph of the given graph, which has all the nodes but does not have any cycles, which is a subgraph of the given graph with no cycles. That is the spanning tree. So the purpose of this spanning tree, right? I mean, the minimum spanning tree is used in many scenarios. Those practical cases, everything will come to that. But the one thing with respect to Dijkstra that we have seen, and with respect to Floyd-Warshall, can you tell me one basic difference in the approach that we had for Dijkstra and for Floyd-Warshall?
No negative cycles.
Negative cycles is one thing. With respect to the strategy that we use, the programming strategy that we use, is there anything which clearly distinguishes between the Dijkstras and the
Floyd.
Floyd-Warshall?
You don't update visited nodes in Dijkstra.
Correct. That is correct. Yeah. So the thing is, in Dijkstra, you are actually taking certain local decisions. See, you are looking at your neighbors and you're deciding, okay, this is the best one, and then you do not revisit it anymore, right? So local decisions, which are the immediate local decision which you think is good at that point, you are actually taking that min of in the first line, that new next v, right? The min of whatever are there, the distance, right? So from that you're taking the next. So what if this edge does not, I mean, the edge that you've chosen is possibly, see, you have chosen 2 and there is the one other one with 4. Maybe if you had chosen 4 and you would have had a shortest path to some other vertex, right? But we have
Greedy
proven
approach.
that that is
That
a
is greedy approach.
greedy approach, exactly. So that we call it as a greedy approach, and with greedy programming is one of the very well studied programming strategies. It does not work in all cases. There may not be a greedy algorithm for all kind of problems. Even for all efficient problems, it may not have a greedy strategy. But Dijkstra's case is a very typical example where you study the greedy strategy. In the case of the spanning tree also, we study 2 algorithms. The Prim's algorithm, which is again based on the greedy strategy, and the other one, the Kruskal's algorithm, which is based on greedy strategy. So given a graph, how do you construct this tree based on making some local choices, right? Local decisions that you take based on the edges that are attached to a vertex. How do you ensure that, how do you prove later that the choice that you have made as a local decision, you have no idea, it could be a 1 million node graph, right? You're seeing 6 or 7 nodes, it's very easy for us to understand, but this Dijkstra's work even for a 1 million node graph, right? So that's the beauty of the whole I mean, that's the beauty of the correctness proof that you give. This works for even if there are 1 million rows, 1 billion rows, 1 million nodes are there, it still works. So please go through the proof of correctness of the Dijkstra's algorithm. It's actually a very beautiful proof. Again, the proofs we are not covering because from the course, exam perspective and even otherwise, it's not like, really, probably will not be testing you on that. But anybody who is working on algorithms, you must necessarily look at proof of correctness, because how do you know that Dijkstra's always gives the correct short output? How can you say that, okay, Dijkstra's come up with this algorithm, but why should it be correct for a graph with 1 million nodes, right? That's why we have this proof of correctness in which you take arbitrary vertices. You are not saying the source vertex, first vertex, second vertex, third vertex. You're taking arbitrary vertices and saying that, okay, there is this part which I've completed. Now the next decision which I'm going to make, the local decision, the greedy decision I'm going to make, is going to ensure that I'm going to get the best choice. That's the beauty of the proofs. Taking arbitrary vertices and showing that this kind of works. Okay, so please go through the proof of correctness. We will not have time to look at that. First thing. Secondly, this greedy programming, greedy strategy, again the dynamic programming, divide and conquer. These are all like different strategies we will come across. Just familiarizing you with all these things so that when we actually start with these things, you can kind of relate to, okay, I've seen this somewhere before, right? So yeah, I mean, just if you're feeling enthusiastic about it, you can read so many. There are so many algorithms book. The Bible that we all look at as the CLRS book, the Corman book, which we call it as like. So you can go through that.
Where to go through, ma'am? This correctness?
Sorry, where to?
Where to go through for checking the correctness?
The proof of correctness. That is there in
Yeah.
lectures. Sir's lectures, it is there.
Okay, in the lecture only.
Uh-huh.
Or in the textbook. Well, what have
Textbook
been
also it
suggested?
is there. Textbook also is there, but it's given a different approach using priority queue and all that. So it might
Okay.
be a bit
Okay.
tricky. But just go through Sir's lectures just to get an idea. See, after studying
Okay.
algorithms, if you say I don't know what proof of correctness is, it doesn't make sense, right? So you're coming up, you're
Okay.
proposing an algorithm, and you're saying that
Hmm.
whatever be the input, however many nodes might be there, it still works. For a 1 million node graph, Dijkstra's algorithm works. And if you are asked to come up with a solution, and you have to say, you have the responsibility to show that, okay, this works for whatever input you give. Of course, if it doesn't work, you have to say. Dijkstra clearly says doesn't work for negative weights.
Hmm.
Okay. Yeah, so just wanted to give you some idea about it. Okay. Yeah. So thank you everyone. So we'll continue the next session. Okay. Yeah.
Thank you, ma'am. One thing, ma'am. In the
Yeah.
after this week 5, week 6 will also continue on the Friday because the queues is also there. So we are.
I think we'll have one revision session. I think the week 6, I think we might postpone it to the next week or something. I
But
have to
where it
check
is,
with Atul. Atul decides.
yeah,
Yeah, sorry.
in the schedule, please suggest them, give the pre-schedule so we can plan according to the. Otherwise, we have to leave
Okay.
week 6 because for the revision we are not getting the time.
Correct, correct. Okay, let me check with Atul. I think week 6
Yeah.
we'll be having after the quiz. Week 6.
So please announce it so that week 6
Yeah,
will be the
I
session.
will. Yeah, I will inform.
Because we are not planning. We have to live there.
Got it, got it. Yeah, got
Week
it.
Okay.
5 assignments itself are postponed after the.
Yeah, it's on 19th, right?
Yeah, it's on 19th.
Yeah.
Yeah.
Okay. Thank you. Good idea. I could not
Thank
see
you.
that. Okay.
Yeah.
Thank you.
Okay.
But
Thank you, ma'am. Good night.
Thank you.
why
Thank
do
you,
we
ma'am.
have the course now?
Yeah, sure. Thank you. Yeah, sorry.